up with new ways to test codes, to assert characteristics of codes, and so this is the guiding topic for this first discussion section, or rather brainstorming section. Session is fundamental code characteristics, and we just did a little brainstorming ourselves and came up with a short list of what this may possibly mean, or what we might mean by that, and maybe we can add to that, and if anyone has an idea what they think is an important property of the code to preserve, or I don't know how we kick this off.
Sure. Maybe just walk through the list quickly. There's one more slide which discusses fundamental test problems. I think through the week, the idea is, my impression was to develop complex tests involving turbulence and other 3D problems for which we may not know the exact solution. But to start today, we just thought we would talk about, stay away from those problems and talk about the simple test problems and simple code characteristics. So if we put together a shopping list of different things, completely different things that people do, or different ways that people do the same thing, this seems to be our list. And I kind of broke them up into basic algorithmic issues, like whether you're doing finite differencing, finite volume, or discontinuous for and so on, versus things that are part of those methods, like whether you're doing reconstruction of primitive variables and conserved variables, and what are limiters you're using. That's only really relevant for some of these algorithms. And keeping div equals 0, is that an important difference between codes? Whether you use split run split integrators, that's really related to the issue, I think, and how you solve it. Whether you're using AMR, SMR, and whether you're using cylindrical or Cartesian grids can be an issue. And all of this is just for the basic MHD algorithm. If you start doing gravity, this can change everything, because do you add gravity as a source term? You add it as a divergence of a stress tensor, you get a completely different algorithm depending on how you implement that. And if gravity is important, it might overwhelm all these other differences, so you have to sort of really worry about extending it. So I don't know, there's this slide of properties, and then there was the test is nothing more than what the test that many people have already shown and think about, which is advection tests, linear convergence tests, in which you look at waves propagating in both directions and in a moving medium. Nonlinear, strictly polarized alpha wave, which many people use, shock tubes, and linear regime instability. Linear because the nonlinear regime results in turbulence, and that's for later in the week. But obviously, driving turbulence from instabilities and then comparing the results is obviously an important issue for this workshop. And all of these should be done in multi-dimensions with no symmetry in the mesh, to be fair, to compare to a real application. So anyways, that was what we proposed as being some of the fundamental code characteristics and fundamental tests you might do. And does anybody have any comments? Well, good. So it's 4 o'clock and
oh no, we shouldn't mention the barbecue before we I have some more specific things that came up during the earlier talks. One of them is recovering a Kolmogorov cascade or inertial range spectrum, and then also how the dissipation range spectrum looks, how steep the fall off is. Somebody mentioned that you can tune your hyperresistivity or artificial viscosity to actually, in a finite difference scheme, to adjust this to a desired behavior. And I think Orke, that was you, right? So what is the idea behind that? Why? I mean, usually the things that you're interested in is like the outer scale of the turbulence that will make your mean field effects, your integral properties of the flow, and they should ideally depend on the dissipation. So if you have this,
the idea is that this really reveals the resolution of the code. If the power spectrum starts dropping off a factor of 3 earlier in one code, it shows that it has not the same resolution as another code.
But then,
and also it's a little bit interesting to see what the bottleneck effect does in different codes. If it actually responds to the sharpness of the drop-off, maybe you might think that sharper drop-off would lead to a sharper bottleneck effect, conversely. So there's both a simple cost to run. The only difficulty is to agree on a driving factor. Driving mechanism.
Forcing mechanism.
Despite saying we weren't going to get into turbulence, because that was later in the week.
Yeah, that's right,
I
yes.
mean, I think these are important issues. I mean, number one is, do we really know what the answer is supposed to be, so that we all agree that the bottleneck is supposed to be here, or this big, the wave numbers are this big? I mean, I read papers that say different things.
The experiments will contribute to understanding that.
Yes.
If it's a robust behavior that's the same in all codes, we can start believing it.
I think we need a
If it is
resolved
very much
solution
different
to
codes,
know
we should
what.
be more skeptical about the effect itself.
Maybe Jim is right and we should postpone that. It's actually a very fundamental thing. I was actually more aiming at artificial viscosity versus some truncation, like in a Godunov scheme where you're averaging will lead to some sort of dissipation, and how well that is understood, how well that is controlled, because there are no free parameters in a Godunov scheme. And
indeed also another reason for proposing this. So one of the problems with the slope limiters in node schemes is that they're actually care about slope 0, which may not be visible. And in turbulence you have all kinds of gradients up and down, and these tests are good in that they challenge the slope limiters of the codes.
Right, I mean, I'm not saying that turbulence doesn't formulate a good test problem. I mean, that was the whole point of this week, in my opinion. But I do believe that finding that test problem is very difficult. For example, I mean, again, this is for later in the week, maybe driving is not a good way to do it, because how do you know that the driving itself isn't changing the dynamics?
As long as you have a well-defined answer, there is a well-defined answer.
No, because you're adding terms to the equations that different codes will discretize differently, and where we're changing
I think
things.
so. You're driving at the
Great
larger scale. I
discussion.
mean, that's a completely simple driving. This is sinusoidal force. This cannot be represented differently in different codes. That's the most simple thing to.
Here's my concern. You know, turbulence is described as a product of three-wave interaction, might involve long-wave interaction, but you're not conserving that interaction by putting a forcing it. You're actually changing wave numbers by.
No, that's worrying too much. I mean, any kind of driving at a large scale gives a turbulent spectrum. It doesn't really matter too much what you do. Whatever you do can possibly cause a little bit of a wiggle at the lowest wave numbers. So we experimented with how to choose power in K2 relative to K1 to get a clean slope. And we know that should be about K to the minus 2. But if one doesn't do it, it doesn't make much difference in the actual regime where you don't drive. It affects those two wave numbers and nothing else.
Let me give a counterexample. If you drive it with a solenoidal forcing function versus a compressive forcing function, you can get different answers.
Sure, we'll just
So-
decide on one.
Well, but
So yeah, the question is how universal turbulence is really in terms of that. You also mostly run at intermediate Reynolds numbers, and you might have intermittency there, especially if you have magnetic fields, shear flows. So, but let's actually postpone that to the discussion.
I think we need something that's more complicated than these shock loop
Yes.
tests.
absolutely, of course.
I mean, they are the mandatory thing that each code needs to run
Yeah,
through.
exactly.
But then I
Yeah,
think
we need
it's
something more, of
interesting
course.
to actually look at where there's disparities between codes and then find reasons.
More people.
Yes.
More people.
Yeah, so a ridiculously simple test, but one that gets at some of the really fundamental things about how the discretization happens. I think it would be really easy to do this one. Just kind of a shear flow like you would use for a smooth Kelvin-Helmholtz problem, but with no velocity perturbation across the stream. And the reason that's interesting, and line it up at a funny angle to the grid, and the reason, that's really quick to run for everybody in 2D at like 256 and 512 squared. Everybody can do it tonight in their codes. And then the statistics that you run off, the statistic you run off is the maximum value of the cross-stream velocity, which shouldn't really come up at all. But in SPH, and I believe in unstructured mesh codes, like if you run this in a repo, you should be getting some cross-stream noise that's coming from the either particle motion or grid motion. And depending on how the finite volume code is written, we may or may not get something showing up. And I'll talk about this tomorrow in the Kelvin Helmholtz talk, is that we think that that's got something to do with why in subsonics, SPH, Kelvin Helmholtz is damped. In some of the, particularly in the now obsolete SPH formulations.
When you say shear flow, do you mean a shear flow which is sinusoidal?
I think it might be better to go with something a little bit steeper, like a
Arrow function or
I'm asking this because we mentioned already, I think Oka mentioned not just the Kolmogorov flow. Or did I misread your
No, I think okay mentioned the Kolmogorov spectrum.
Okay, but because the Kolmogorov flow, of course, is a shear flow, but it's there's a wave number that is either 1 or 2 or higher, or 8 or something. And that, I think, might be a common ground for many people who have no idea. So that's supposed to be the forcing function?
No, this is not. This is the initial condition.
Right.
This is just QE hydro, let it run.
Yeah.
And it sounds trivial, but it does different things in different codes.
Yeah.
And this is actually really bad for touching off things like if you in your SPH, if you have pair instability, where the particles stick together, this is really bad for touching that off.
But how do you know what it's supposed to do?
There are no perturbations here. It should just run smoothly. This is just fluid going this way and fluid going this way. There's no cross-stream perturbations, so nothing should.
Oh, but you might
Cross-stream perturbations should be identically zero, so they should never
become
cross.
unstable.
Sorry?
It must become unstable.
But that is from grid effects only. So that will have a
linear
different
shear flow is non-linearly unstable, right?
But even then, if you have no perturbation, it will not go.
This is linear stable, but your
It has an reflection
linear
point.
stability doesn't
Become
mean
unstable.
Eventually, but the perturbations that's growing from are going to be only
Yeah.
numerical ones.
Yeah, but
So
you-
that happens very
no,
differently in grid
you
codes.
can add noise. I can give you an amplitude of 10 to the minus 9. And if you
No, that's a different, that's now a Kelvin Helmholtz test problem. This is what is the noise in from your grid discretization. That varies a lot between different types of
Why is that
discretization.
important? I mean, there is, of course, noise in reality. I mean, from the initial condition, for example.
Well,
And
this
it might
is-
be a grid controlled one, in our case.
Well,
Controlled one.
right, so one of the things in say, some methods have a lot more, so you can run, if you have a smaller grid noise, you can run smaller physical perturbations. And that's the thing, like in traditional SPH, you have these motions that are on the order of the sound
Yeah,
speed.
sure. But in any
Right.
case, it's an unstable problem, and then we want to understand the growth rate.
I don't.
And finally, the saturation state.
That's a different regime than
And
we're
in
talking
your
about.
case, it's decaying, of course, therefore that makes it tricky, and therefore.
Yeah, that's different than what
I
I
think
was
that's
measuring
why-
in this.
I think that's why a good replacement for this would be the Kolmogorov. Maybe Axel can say something about it.
I think we might postpone that to the end of the session. I think one thing that was addressed now is grid noise, which grid people usually don't think a lot about. I think that's more something that applies to particles. So there's always
Maybe if I.
people talking about numerical diffusivity, numerical viscosity, and this is very like a diffuse term. So I wonder if anyone has ideas how to quantify these in a meaningful way.
Well, okay, I mean, if we take a look at the test problems that Jim suggested, we can do the CPA and do the long-term decay and see the decay rate of the transverse components and see how fast they decay. I mean, this is a direct measurement, let's say, of numerical resting.
For our phase waves, but then the question is how far does it apply to just a shear flow or to a sound wave or
Yeah.
to a magnetoacoustic wave? So the question is how universal these
If the numerical distributions are nonlinear, then depending on what you have superposed, you get totally different.
For the test of the intrinsic analytic random number.
Yes.
Yes.
Right.
Okay.
We can try to look at
Good.
Thierry models.
Yes, Jim had some concerns about, yeah, maybe.
I was just saying that you can look at Thierry models and technically,
Yes.
if you are looking at ideal MHD, you should have no Thierry model at
Yes.
all. So I mean, it's a good diagnosis.
Indeed, a good point goes to what Aki said this morning, is that you're not doing ideal MHD, you're not doing ideal MHD.
So it could be a way to probe the non-ideal part of the code.
I mean, we want to have a prime number which is either 1, or it should be 10, or it should be 0.1, or it should be 0.01. It should be input parameter. It's nothing, it's not an output parameter. I mean, if you want to do the sum as opposed to, or for example, a cold disk or something, as opposed to an AGN disk, these have very different product numbers, and they have different behavior.
Ideally, of course, you would prescribe your microscopic dissipation, but that means you sacrifice a lot of your resolution.
Yeah, but how are you going to answer the physics problem then? You're basically waiting until somebody else does it for you.
Well, the idea is that one only resolves the large scales and then assumes that the unresolved scales prescribe a turbulent cascade, and then it's not true that you have a magnetic Prandtl number of 1 over 10,000 or something. Then you have an order unity Prandtl number again, because you're not resolving the. So, yeah. I mean, there's two approaches. You either do really understand fundamentally turbulence at high or low Prandtl numbers, and therefore, of course, you cannot get around doing DNS, and that's very important to find out the scalings. But if you then want to do accretion disk or chat launching or something, you cannot afford to run a DNS, so you need to make sure that your subgrid physics is a meaningful one.
Yeah, but it's a little bit more complicated than that. So there are sort of two communities here. People that care about Prandtl number and people who don't care about Prandtl number. And those people like you who don't care about Prandtl number would like to think that it's effectively 1. So that may be true if you have sufficiently high Reynolds number. That's what we hope to motivate using our mathematical codes with. But it's a more serious problem if you're actually running at 1,000 qubit resolution, but your code effectively has Prandtl number 0.1. You just don't know about it. And that may actually be worse than having a Prandtl number 1, which is what you hope that you have.
Because it might be in some intermediate regime at 0.1, yes.
Exactly.
Yeah.
So it's actually important to know what is the effective Prandtl number of your code.
That's exactly what I meant with this intrinsic
Yes.
PM, yes.
But that's determined by the turbulence itself. And
No, that's
But I
determined
think
by
also-
some characteristics.
no, but I think the turbulence makes a difference too. We're
Especially-
talking about turbulent resistivity here at the end of the day, so that might be quite different than the microscopic diffusivity. And you might want to make the Reynolds number X, but the effective Reynolds number.
Here at this workshop, we have a unique opportunity to actually test the Prandtl number. Because some codes can tune the Prandtl number, and other codes can't. And we can just match them, and use the codes that can tune the Prandtl number to measure the Prandtl number in the codes that can't tune it.
So I mean, this has been done for the MRI. It was
Yeah,
in
this-
three
this is-
groups,
this is
including
known.
Geoffroy,
This has been
measured
tested
Prandtl number,
extensively.
3 different codes.
So I mean, yes, we do have tests, and we know that, well, codes like Zeus, for example, have an effective Prandtl number of 2 in the particular case of MRI turbulence. But okay, then so what? In the end of the day, what you want to know is what is the real life situation, which is certainly not a numerical resistivity, certainly not ohmic resistivity either. So, I mean, so we do care about Prandtl number. The question here, I believe, is not really a physical question. It's to know from the numerics whether the codes have some sort of physical dissipation process. Does it behave linearly, non-linearly? Can we find where is the, in which range we are in ideal MHD and in which range we clearly see numerical artifacts due to the code? And that depends on the numerical technique. And I believe here the questions we are trying to answer are not physical, they are really numerical
Yes.
questions.
Yes.
So, well, yes, we should worry about the quantum number, but that's another discussion.
But and that was exactly the point, that the smaller the Reynolds number, most likely the more important the quantum number is. And since we're running at finite Reynolds numbers, we need to actually worry about it a bit. Until we run at 10,000 cubes, maybe then we can
I
start.
mean, you have said that you basically resolved the issue with the MRI problem. And I'm wondering whether the MRI problem is sufficiently simple to actually address and possibly get an asymptotic regime. I think what Åke said is correct, that if you have a large enough Reynolds number, you should in principle be going to an asymptote.
Yeah.
things
And
should
the answer for the MRI is
not matter.
20,000 cube.
What? How much?
20,000 cube. Well, if you can do that, then, well, fine. In principle,
There was
it should work.
comment in the back here.
Yeah, so actually I like to say that dynamo, it may not be turbulent, but it's quite critical on the Prandtl number, whether it's large or small. It depends quite critically in the whole behavior. So it's not quite an academic issue, I think it's a real issue. And convection, low Prandtl number and high Prandtl numbers have very different behavior. So I think we need to worry about Prandtl number quite seriously. Convection, low PM and low thermal Prandtl number and large thermal Prandtl number have very different behavior, including the spectrum. So I didn't bother too much earlier, but now I see that it's an important issue. Of course, codes are very difficult because we need to resolve both the fields, velocity and magnetic, and going beyond 100 or other way around 0.01 is impossible right now.
Axel has a way where you can push the limits by initiating and then increasing the Prandtl number, right? Because then at higher Prandtl number you get less structure in either the velocity or the magnetic field as you go.
That's right. So if you make the Prandtl number, for example, as very, very small, then most of the dissipation occurs ohmically. And so there's much less energy to be channeled through the kinetic energy channel for a given number, for a given Reynolds number. And so you can actually make the Reynolds number even larger by easily a factor of 10 or 100 maybe in some cases. So I've been able to reach fairly extreme Reynolds numbers in some cases when I am in the regime which is in the non-linearly saturated regime. The question then is, are those results actually correct? And what I get is an interesting, I've had this in 3 papers now, a ratio between kinetic energy dissipation to magnetic energy dissipation, which scales with the Prandtl number to the 1/2 power over 6 orders of magnitude, from 10 to plus 3 to 10 to minus 3. And one might well be wondering whether it's correct or not, but that's at least a result and which one should address, I think. I mean, can it really be true that the ratio of kinetic to magnetic energy dissipation is not just a viscous, a resistive thing, because the magnetic energy dissipation is exactly the same term that is the dynamo term. So if you do work against the Lorentz force, that's kinetic energy that goes into magnetic energy, and all that energy will be eventually dissipated. So it doesn't really matter. Do you measure this at the dissipation stage, or do you measure it at the input stage? It's as well a macroscopic term. Another question is, does this macroscopic term scale with the Prandtl number? And at the moment it does.
That would be very irritating for the first group of people.
Right. All right. I mean, if
I think it's emerging that we always end up talking about turbulence in the end. To just hit on a couple of other points. One thing that might be of interest is actually maintaining equilibria. Often we are interested in studying instabilities that start off a stable state, or we have like a stratified accretion disk, or convection, and the question arises, how well can codes maintain equilibria, and how far does that touch upon whether you have a split or an unsplit scheme? Does anyone think that would be a worthwhile issue to look into?
You have a suggestion?
Like set up a hydrostatic equilibrium and then see how well that's preserved in this would be like a dynamic equilibrium, yes, I was even
Well, that's
thinking
an
of-
unstable one.
It's unstable. The difference is, and I'll show in my talk tomorrow, running that with SPH, and it is interesting to see, because it will eventually blow up in any code, something will serve perturbation, so you're walking right on a knife edge, and it's there, you can get quite a large contrast between different discretizations of how long it goes before something does
But
blow up.
it's also a common wisdom that
You
the
should never actually do science
more
with that kind of
accurate
thing.
your code is, the more prone it is also to amplifying your grid noise and making it less robust. So
It's
if
a
you have a
balance
very
between-
diffusive code, then you might actually
Right, so that's one of the, yes, that is one thing that will happen. So that's why, one of the reasons it's interesting, is that a very diffusive code won't do that so much, which is not necessarily a good thing. There's more than just accuracy. There's a balance between diffusion and where the noise comes from.
I mean, isn't this problem just measuring properties of truncation error in your code?
Yeah,
And
yeah.
If you're really worried about that, then, I mean, you can minimize it so it's spatially uniform and good is probably fine, but then you'll probably introduce some other truncation error. I mean, at the end of the day, you know, truncation error is part of life. It won't go away.
Yeah.
You know, it resolves away. That's the only thing that makes it go away. And you just have to be
Well,
certain
that is
that
one
the
thing, it doesn't-
truncation error
it-
is dominating your solution. If it's dominating your solution, you're in a situation. I mean, usually when one studies these kind of problems, the only well-posed problem is one where you put a finite empty perturbation in.
Yes, that is,
Somewhere,
yeah,
because
that's a
the
well-posed
only
problem
way
with a known
You have
solution.
a constrained mode, an eigenmode for it.
Yeah.
And any other is just super truncation error. Then
But it does, it's a way of actually showing what that truncation error does. That's what's interesting about it. Well, I'll mention it. You'll
It's still
show up
not certain
with
how
my-
that, I mean, you know, there's gonna be truncation error when you have your turbulent flow, it's gonna be there, and extracting its role there is not nearly as easy. You want it to be dissipative, you don't want it to be dispersive. But there is an example where this matters, if you have to hold the equilibrium state for a long time, so if you think there's instabilities involved in nuclear burning on white dwarfs, where you want to hold hydrostatic equilibrium for a very long time while the reaction is percolating. But then there are straightforward fixes to make the particular truncation error that causes lock equilibrium go away, which Singale proposed. So that might end up being a problem-dependent thing as well.
I mean, I think you mentioned again this term, we don't want to be too dissipative or too dispersive. If we do want to resolve turbulence, we want to have a certain Reynolds number. And of course, it should be as big as possible, but if you have a certain resolution, it won't be, it shouldn't be bigger than what the mesh actually can give you. Okay, so that means even if you have a Reynolds number of 1,000, you have to have a certain amount of dissipation. And then I don't understand a comment saying that the Reynolds number of 100 is, or 1,000, whatever you do, is too dissipative, or a particular simulation is too dissipative. I mean, either we do a simulation with a Reynolds number of 1,000, and then we can ask the question, is that really 1,000, or is that not a Reynolds number of 1,000? That we can ask. But it must be dissipative.
Yeah, I agree that the truncation error better be dissipated.
And it must also be correct, of course. I mean, there's possibilities that the dissipation might be incorrect. I mean, for example, you
What does that
mentioned the
mean? What
Woodward.
does it mean to have incorrect dissipation?
What?
What does it mean to have incorrect dissipation?
I mean, the dissipation is often nonlinear,
Yes.
and we don't know what exactly that actually means for the turbulence. So, for example, when we look at this Porter-Woodward Bouquet power spectrum, we had over an order of magnitude a case of -1 scaling, and then we increased the resolution, and this case of -1 scaling became longer and longer. Right? And now the question is that actually physical? Is it unphysical? What
Isn't this
is that?
the debate between DNS and LES?
I mean, I would not call that
Your argument,
LES.
you need to do DNS. You must put in an explicit dissipation,
Yeah, right.
resolve the dissipation scale, and simulate it.
Yeah.
The The LES community says you don't need to do that. You can build a subgrid model which captures the dissipation on unresolved scales in a conservative fashion such that the gross dynamics is unchanged.
But that's a claim,
Yes.
mostly. It's not necessarily always.
Well, I flew here in an airplane that was designed with LES, so I do believe it works.
Well, there's also, at Astrophysics a month ago, there was a lot of people using the term implicit LES for when they were running, as far as I can tell, they were just running God codes and they're claiming that
Yes.
the
If that's done a lot, that is why I actually had the idea of really this frontal number thing, because a lot of the dynamics will eventually depend on the frontal number on larger scales.
Actually, I think if you're using LES, you cannot really address any fundamental question. Because whenever what people do is, they do a DNS, do an LES with lower resolution, and then they say that these two are consistent in the grids that LES is doing, and that's fine. But that means that you always need a DNS to compare
Yes.
LES against.
Right.
And about using LES in an airplanes, before that they used to use K epsilon, and they still used to fly. Right, so that's my
Nearly always.
Sorry?
Nearly always.
Sorry?
I think they use wind tunnels.
Yes.
That was much more reliable. Sorry? I mean, it's certainly true. The issue with using LES and astrophysics is we don't have wind tunnels to calibrate our subgrid models against. How are we ever going to come up with a subgrid model for MRI in weakly political plasma? Unless you have the right subgrid model, then your LES isn't worth anything. But it's still a conceptual issue, I think, whether
So maybe the,
clearly generates strong feelings.
maybe the question should be that if you have, for example, to again go back to the question about the bottleneck that Oke raised, maybe finite volume codes will not give the right bottleneck effect. But maybe in many cases they don't care, because what they want to really reproduce is the small scales behavior. And the
large
bottleneck
scales.
is, sorry?
The large scales.
I'm sorry, yes, I was always thinking of Fourier roots, sorry. Large scale behaviors. And the bottleneck is really at the border of the dissipative range and the inertial range. And if you don't care about that, maybe you don't need to worry about that. But even then it is good to know that it is, the codes are not good enough to talk about such things.
Axel?
Makes sense?
About that one, you do of course get magnetic fields by dynamo action. That depends on the particular properties of the dissipation.
Do we know that as a fact, that all dynamos in astrophysics
So I'm talking about the small scale dynamos.
Sorry?
There's two different things. There's either large scale or small scale dynamos, and the small scale ones certainly do care about the particular values of quantum number, at least within certain ranges.
And there's also a paper that shows when you use hyperresistivity that you get the wrong saturation level for the dynamo, right?
That's also correct, that for a dynamo in a closed system.
That's one example where actually the microphysics, the truncation or the dissipation would affect a physically meaningful result that you want to study, right?
Yes, right. Actually, one comment I wanted to make at this point about LES. In the turbulent combustion community, LES is regarded as, of course, a very important thing, but it's extremely complicated. It's not at all anything simple. And so, I mean, if we do an LES which is tested and well elaborated, of course, then it might be great. And then, of course, it should be challenged by people, and they hopefully all agree that this is indeed a good LES. We certainly don't have that in MHD.
Right.
And I'm not sure we have that really in isotope homogeneous turbulence very well.
Right.
I mean, we have it for airplanes somehow, but that's also not exactly homogeneous.
There are simple hydrodynamic LES models, which are, I mean, I'm thinking about the Scholler-Lussier models, for example, in spectral space. These are quite simple, and they are MHD extension, which exists. I mean, they are not totally successful, but they work for some problems like decaying homogeneous MHD turbulence. This has been shown to work. So
by Müller, yeah? Or what?
it was by the group of I think Fouquet and and all those.
First of all, okay, I'm not exactly sure with that particular paper. I know the similar work by Müller. They had fairly small Reynolds numbers, and in none of those problems was a dynamo action. And I've seen that in a few cases.
I'm not talking about dynamo action there. I'm talking
Yeah, well,
about
I mean, the
an
dynamo
image
will occur.
distribution.
Once you have a Reynolds number big enough, there will be a dynamo. And of course, if
But
you force yourself to do low Reynolds,
I'm talking about decaying MHD turbulence. There is no dynamo.
Of course, there's a dynamo. Decay. Right?
Right. Okay. Okay. So
Depends on what is faster now. And
When you have an inverse cascade of velocity to larger scales in the
yeah, you have a transfer of energy into a magnetic energy.
right, but the thing is decaying. Okay.
Let's see what
My point is just that there are simple LES models available on the market.
Yeah.
Right? You don't have to, of course, there are very complicated models, but there are also simple models which can be, tried on some simple situation to see whether or not we can get a meaningful answer.
And by
Of
simple,
course, it's not.
sorry, can I ask, by simple, do you mean is that you have a viscosity which is actually going up with the current density or something of that type?
You have a viscosity and resistivity which depends on the properties of the turbulent cascade which is above it, for example.
Yes.
What is typically in Scholler-Russell? I mean, it's typically this sort of thing.
Actually,
So-
I think that's for me, the MHD, the problem is we're not sure about spectrum.
Yeah,
Then it becomes LES is somewhat uncertain because we don't know the spectrum.
sure.
And that's,
So, in MHD, for example, we were talking about the quantum number issue, and you were talking about the small quantum number unit. A hydro LES model would be perfect because you could resolve the MHD cascade down to the resistive scale and then inject your LES model below the resistive scale, in which case you have a pure hydro cascade and everything is fine. And you are using a model which is used in airplanes for your MHD calculation in the limit of small PMs. So that's a typical example in which you can actually try to do something with LES, right? It's not unfeasible.
Maybe another way to say it is that the fact of the matter is we will never reach the appropriate parameter regime for the microscopic dissipation in most astrophysical flows. Moreover, it's not even ohmic dissipation in most astrophysical plasmas. It's something much more complicated. It's not even clear what the Prandtl number means when you're talking about an accretion disk. So in the light of that, is there anything useful that we can learn from simulations? Period.
actually, I have one
And I think
solution
that's a
for,
fundamental question that, that everyone here, I think is already answered implicitly by being here, right? Yes, we think there is, but maybe, some reality check on that would be what's really discussed.
yeah. So the energy flux for fluids is cosmograph flux, but a similar thing for MHD. So we do a simulation for, let's say, 1000 cube and do for 256 cube, and the flux must match for whatever wave number range available to us.
Yes.
And that I think is the most stringent test for LES or for low resort simulation. I think that nobody does it, but I think that
Yes, that's what we did with the pencil code, we checked.
The DNS simulation
Yeah.
at some extremely high resolution of a problem relevant to astrophysics that we compare against, just to make that first sanity check. Do you get the same answer as DNS at the resolutions you can achieve in normal codes? That's sort of a zeroth level consistency check. Doesn't mean to say you can necessarily probe those small scales with those codes anymore, but it would at least be a zeroth order consistency check that would give us some confidence in going forward, because we're just never going to be able to do the actual problem ab initio. That's just fact of life.
Yeah, so that's something I will try to suggest tomorrow, at least for the title part. And actually we have something written in the wiki that's along that direction.
Okay, I'll try to pull this away from turbulence again and raise the issue of divergence B constraint and different algorithms, and especially in the mesh-free codes where usually some sort of cleaning is introduced. And then we had the question earlier that I think we should follow up on whether divergence B errors in how far they really spoil the result, and if they can be considered small in any case, or whether they really should be zero.
I'm going to comment on that on Wednesday on my SPH MHD talk. So, but I mean, from the test that we've done in the group, it looks like that And for many problems with SPH, it doesn't make a big difference if you even clean. So often you can just leave it and control the error and say it's a few percent. And so like for an Ortsack-Tang vortex, for example, if you do something like a Debner cleaning, which is really not so easy to do, I think, there isn't a big difference. But then comparing to Athena, there was still a difference. So I don't know, and I don't have enough experience to know how, if that is, you know, made in stone and is correct in any
There's probably
case.
a lot of other things that are different between the calculation beyond just the B. So it's hard to know whether that difference is from other things.
But I mean, in terms for SPH and for many problems, you don't, I mean, as appears to us that you don't have to worry too much.
I didn't want to, I mean, there are grid codes that use the 8-way formulation and require some sort of divergence B cleaning, and they say, oh yeah, we just smear it out over the whole thing, then it will not do anything bad anymore.
But is there a way to test? Is there a well-defined problem?
Gabor-Todt had a paper where he looked at shock tube tests and different methods, and you see all sorts of spikes in especially magnetic field angle at the interface would be very poorly defined in these schemes, but then it comes down, yes, the shock region, if you integrate over, will that be a significant Lorentz force?
Mario, you had a paper comparing different methods for
Yes, so what I can say is that, I mean, if you use 8-way, for example, in combination with the roll solver and the monopoles which appear stay a bit low, I would say it's completely okay. So you can use these methods. But on the other hand, I mean, you will see it directly. I mean, if B grows above a certain value, I mean, you will have, I mean, directly effects. In this simulation, it's clear. I mean, the mass will accrete and you will violate everything. But yeah, I mean, I'm not sure how far we can use this Debner cleaning method, because what I have experienced in turbulent simulation using Debner, I mean, I was not able to clean, because if you have turbulence and use some method like 8-way for Debner, you steadily create these monopoles and you cannot get away. So for turbulence, I really have no alternative than CT.
So we've been looking at in terms of the Ortsack-Tang vortex. Is that a good test for something like this? I don't know, for grid codes?
The Ortsack-Tang vortex, that's standard.
Yes.
Or what kind of test can you use to look at it if we,
This was an MRI test, right?
That was an MRI test,
Okay.
yeah.
Maybe
So
it would be nice if there were a simpler test. Maybe these,
But
again,
suppose-
Turing modes would be.
Supposedly the Ortsack-Tang test is sensitive to degree.
Sorry, it is? Is it?
Yeah.
Okay.
Because it generates lots of shock intersections and so on, and it sort of explores phase space.
It's a decay problem, right?
It has a,
Yes. I mean,
an intricate pattern, but still reproducible, at least for quite a while. So if there is a small defect somewhere, it will show up.
This is sort of relates to all the tests. Maybe particular diagnostics from Ortsack-Tang are useful. Just looking at the picture, I've found in the past isn't always useful. I've run the problem by mistake with magnetic field incorrect by the square root of 1/4 pi, and you couldn't really tell the difference. At least a time and a half.
It makes a clear difference.
In 2D or 3D?
It's just 2D.
Yeah. Somebody was telling me that in 3D it should actually stay 2D, the whole thing. Is that correct?
Unless you put in perturbations, sure.
But even
because
with perturbation,
you can do a 3D Ortsack-Tang with a VZ that has some dependence on Z.
But no, only perturbation-wise it has perturbations in Z, yes. But do they grow, these perturbations in Z?
Sorry, so you're asking doing an Ortsack-Tang vortex test where dV, x, dz, all quantities is 0? All quantities are symmetric in Z?
Yeah, and then you perturb.
Well, then you perturb it.
And then you ask whether the 3D perturbation actually grows.
I don't know anybody's done that test. I mean, it's planar shock waves you're going to generate in planar flow, so yeah, there'll be some small, but these are not instabilities that will be amplified as in Collins tests, so I wouldn't expect dramatic 3D evolution if you don't.
So with Ortsack-Tang we have a maximum of participation after time 2 or something, right? That's at least one thing I remember somehow.
That's a good question. I don't recall the evolution of dissipation in time.
And then
Did you
the
plot
question
that?
would
I
be,
don't-
what
I'm
is
not a
known
paper
about Reynolds number dependencies in that case?
So I mean, in terms of a DNS test that we could all compare against, maybe a 3D version where it's like Kang. And I personally think starting from an analytic initial condition is the best kind of test as well, because then everybody can agree on exactly, and they can
Yes.
work in their own code how they should want to initialize that exact
Yes.
initial condition.
Yes.
That's the advantage of Morse Kang, is it's an analytic initial condition.
Yes.
So if there's some way to make it a 3D turbulence problem, and there's some way to do a DNS, then that would be.
That's
Maybe
maybe
we should
in your
have a
homepage.
DNS
Right?
with
You
short
have that one, of course, in your homepage, isn't that right? You can maybe just remind us and write it down on the whiteboard, blackboard.
What the initial conditions are?
Yes.
I'm sure I can't write it down on the blackboard because I don't remember exactly.
But it's on your homepage.
Oh,
What?
Yeah.
Two questions. Actually, there is no thermal instability in the list here.
Sorry?
There is no thermal instability here in the list here.
Which instability?
Thermal instability, it has the convective instability or
Right.
the
Yeah, sure. That
thermoacoustic
I had done,
instability.
so I mean, I hope it's-
And the other question is, remark, it's why we should have all the time multidimensional problem, because 1D test can be also a good test. No?
Indeed, that's where you should always start, in my opinion, but I think it's also misleading to only show 1D results, just because codes perform better in 1D than they do in 3D. For example, the div B issue
Yeah, but I
it
say
doesn't
that-
exist in 1D. There is no such thing as a div B
I
issue.
say that because having the linear growth rate in 1D, it's sometimes much more simpler than in 3D or in 2D. For example, I know for example,
Right.
the thermoacoustic instability, which is a good test
Right.
between radiation
Right.
and hydro. We know the growth rate in 1D, but not in
Right.
2 or 3D.
So, just to be, I wasn't very clear, what I really mean are these are 1D problems, but they're just rotated on the mesh. So you can still use the 1D growth rates to measure the dynamics, but the evolution will be in multi-dimensions. So for example, the shock tube problems are intrinsically one-dimensional shock tubes, because we don't know multi-dimensional shock tube solutions, but they are rotated at the mesh so that you actually exercise your algorithm for keeping div B to 0 in shock tubes.
Going back to the div B issue, one of the things that Bradfield and Barnes pointed out back in the 80s was that not preserving div B 0 leads to artificial growth of the magnetic field.
What?
Leads to artificial growth of magnetic field.
Yeah.
And so one interesting test, I'm not sure what it would be, but it would be interesting to do is to see, to compare the growth rate of magnetic fields, different codes that treat the divergence of B differently. And because the growth of the magnetic field is an important problem in many applications.
Especially yours.
There's like a simulation of galaxy formation now, where strong field growth occurs, and then it would be very good to back up that this is actually not affected by the percent level divergence B errors. Yes. Okay, to wrap up, there's one last bullet point that we haven't touched upon. That's angular momentum conservation, and that's in Cartesian grids. So obviously, if you have a certain symmetry, like you do a star or a accretion disk, you can always adopt the curvilinear coordinate system, where your angular momentum with respect to the star or the center of the star is conserved analytically or to round-off error. But what you come across if you do simulations of galaxy formation in the cosmological context, or formation of protostellar disk, when you have a collapsing molecular cloud, then the disks are always very poorly resolved, so you're always at the resolution limit. And then angular momentum conservation is very poorly warranted, and so you always end up with disk profiles that are not quite correct, and you have central cusps and all sorts of errors. So do you think there's a need to define the test problem to actually measure how well angular momentum is conserved in a code?
Yeah, that's a
And
big issue.
it should be one where you have variable orientation.
Okay, that's already very complex thing, and ideally one where you possibly use self-gravity, but we've come up with a simple situation where you just have a 2D rotating flow with a central force, so that would be a dynamic equilibrium. But then you of course have the problem of discretizing the central force in balance to the centrifugal force, so that's not quite clear what error that will introduce.
So one technique that we could use is if a problem definition is simple in principle and can be coded in IDL, then I can of course easily rotate the coordinate system with the coordinate transformation and obtain the same initial state in any chosen orientation and then give it to the code. So one doesn't have to write it in the code.
Oh, okay, no, that's not what I thought of. I was just thinking as simple as possible starting point to really have, already as I said, the central force discretization error will play into this at some level. We figured out that even just upwinding, if you just do a simple advection scheme with a constant density, circular flow on the Cartesian grid, you get a quite dramatic advection error just from the upwinding.
Sure, but it's still important to be able to test different orientations because
ultimately, of course, yes.
A simple setup will by definition be one where you're aligned with an axis.
But even in 2D, you have severe violation of. That's because on your discretization scale, the grid cell, you actually enforce linear momentum conservation, and that to round-off error, and then obviously it's very hard to advect something around the corner when you only got the.
I think the IDL script gets complicated with finite volume because you have to integrate the initial condition over the volume of each cell, and so you've got this complicated mapping between the cyclically symmetric solution and the Cartesian mesh, which has to be done all properly to get the volume average momenta initially. But I just I think it's a good idea to have an analytic condition that you can then make as complicated as possible by rotating it so on. And you could extend the test not just to angular momentum, but what about other conserved quantities like magnetic helicity, which is something Axel has thought a lot about. But I don't think most grid codes that I'm aware of conserve magnetic helicity per se. Are there test problems to demonstrate this? I worry, is this even a conserved quantity in the turbulent flow?
I think that
IDL and HD, yes, but in these.
I can imagine that there is a very simple test problem if you accept to do a problem with a finite magnetic diffusivity.
Okay.
This problem does not exist with zero magnetic diffusivity because we are talking now about violating magnetic diffusivity by the resistive term. So all you do is you force your system with helical driving at a small wave number, at a high wave number, sufficiently large compared to the box. You will generate large-scale magnetic field, and the large-scale magnetic field eventually will be one of a Beltrami type. It will be a sine wave in one direction, a cosine wave for the other component in the same direction, and no component in the third one. That will be the final state, and the time at which you reach final saturation is a well-defined time scale. It has to do with magnetic diffusivity. The reason for this slow growth on the resistive time scale is magnetic field conservation. So if you screw up magnetic field conservation or modify it somehow, you will get a good different saturation law. So I think that is a very simple test, and you can use fairly low resolution for that.
I guess the theoretical issue is you actually don't need to compute it immediately. You can just look at the energy.
Yes, exactly. You don't actually need to calculate the energy, you just run the energy. And for example, you can do a problem with hyper-resistivity, right? And you can actually predict how wrong the result will be. You will get a larger, as I think you just said, you will get a larger separation amplitude as you can predict from hyper-viscosity or hyper-resistivity calculations. And the numerical code should get this wrong result, which you can predict. On a different time scale again, of course. It's fairly straightforward, it's hyper. And then there could be more complicated diffusivity schemes, which I don't know. Oh, that's how
beautiful weather for the barbecue.
What?
Beautiful weather for the barbecue.
Yeah, but it's so strong that it will also go away again. So it's good. And I think they have already heated up the barbecue, so I really
No going back now.
We go outside and
hot air to evaporate the rain that buffers.
disabilities.
And then you check on the edge.
Or you have a question?
He's just tweeting.
So I think actually that's an interesting test problem because it explores what's often said to be a very important property for MHD dynamos, but it's poorly understood in finite volume codes, for example. Is how
Yeah.
well it really does.
Right. As I said, the type of forcing that I like normally is isotropic, homogeneous, and random one. Many people actually do the same problem with ABC flow forcing. You could do that same thing. I have not actually done so much with that. But if we agree on that, we could do, of course, or some of us could do such a problem until tomorrow or something. So an ABC flow is clear what that looks like. And you take an ABC flow with a forcing wave number that is somewhat larger than the box wave number. So you take a box of 2 pi by 2 pi by 2 pi, and then take a forcing wave number of 5 times the basic one. The basic one is 1. So you take a wave number of 5, and then ABC flow, and you should get n more. You just run it with with not too high Reynolds number, otherwise it will take too long. But it's a resistive time scale. All right. Who wants to do that? You sound like one.
I would like to do that.
Okay.
Well,
And many such problems can be done at 16 cubed. 16 cubed.
If you have a high order code, yes.
Yes. And otherwise you would do 32 cubed. Well, you can even do it at 8 cubed.
You can do 4.
Get an error of 30%.
Yeah, so I think it's a good idea to get standard initial conditions and just do the decaying one and keep it as a report for testing. Right? I mean, ABC flow or in fact Taylor Green or that's what is it? Tong what is that? Taylor. Yeah, that's right. Yeah, I have it here. So some initial condition we can put, and the decaying will be deterministic. We can just
Decaying would be what?
deterministic. I mean, in the sense, every code should have the same decaying pattern.
So you get it, or the word.
Deterministic.
Deterministic thing, yes. Yes. Okay, so we do also time, we do ABC flow driven ends. It's A and B and C equal to 1.
Well, the Norsec tang still yet to be formulated in 3D, and what the answer is supposed to be is
Yes.
not clear.
I looked at your webpage, there's a lot of 4 pi factors around. Is that good? Especially after you said you might make a mistake with that.
Well, that's why I made the mistake.
No, we have the test paper, so I can show you that. This is that tank, Aussic tank. I have the plot, and it basically comes from Karate's paper. So we reproduce that.
Can you show us in this
Yeah, okay.
page maybe?
But you could kill some time with brain stops, I guess.
Story time.
Yeah, so that is a evolution of chemical and the form of the, this is the initial condition.
That's the initial. Oh, right. Okay, that's your paper.
Oh, you have it.
These are preprints, rather it's under review, so yeah, I can send to everybody.
It's on the archive.
Best you can
Yeah,
put it
from-
on the wiki, we have a wiki
Okay.
page, and you can create
Yeah, yeah.
a sub-page for that.
Okay.
Yeah, voting.
It's divergent free, huh? The
Sorry?
velocity. The velocity is divergent free, no?
Yeah, it's an incompressible.
Yes, it's come from Business. Okay, yeah.
And the reference is that paper 16. So I can also show you that. So I will upload in the wiki.
So far we've only talked about standard MHD and dissipation terms. Is there anything related to more non-standard terms like radiative cooling, heating, or radiative transfer, heat conduction, that anyone thinks would be worthwhile to check in a quantitative way? So somebody mentioned that one problem with the Godunov codes and the Riemann solvers is that as soon as you have non-standard like equation of state or thermal physics, that your characteristic speeds will change, and that's not accounted for in the solver. So, for example, you can run a adiabatic setting with a energy equation, and then you can have a radiative cooling that operates on a very short time scale, which will make it essentially isothermal, and then you would expect if you do a shock tube that you get the isothermal speed rather than the adiabatic. And there have been arguments that this then should be incorporated in the solver rather than be treated operator split. So that's the sort of thing. Exactly, yes. That was one example that came to my mind, but something along these lines where how easy is it, because now we're moving on to very complex physics with the Hall term and bipolar diffusion, how easy is it to extend standard schemes with non-standard physics? Can you just do operator split, or will you have to do more intricate modifications to your scheme, and how well do different schemes handle this kind of extension?
It really depends on the problem, I guess. But I think for the applications I was interested in, you can handle these stiff source terms quite naturally, incorporate them in a Godunov formulation and modify the characteristic structure of the equations without too much. Without too much messing up the code too much. It's actually relatively clean and simple. And in some cases, for example, in the case of the particle is coupled with the gas, which is happens in perfinite disks. I think it's probably one of the only ways to treat the problem. I don't know how else you can actually solve the problem accurately. But it captures all the nice things that you capture all the physics very naturally and quite accurate.
That's actually something we haven't talked about at all, like having interaction with particles, which is both interesting for cosmic rays and for dust in protoplanetary disks. So Anders already left, but maybe it would be worthwhile to also think about a test case, like a linear mode of the streaming instability or something that one could.
Yes, that's done by Andrews and others. The problem is that linear modes are very difficult to compute. You have to do it so numerically, and so you rely on people to present tables of modes.
Oh,
So that's something you're going to do by yourself.
That's maybe something like have a centralized, like a virtual observatory,
Sure.
where you have both initial conditions and test solutions.
So Andrew Uden and Andrews have published finite set of eigenmodes for the streaming instability in their papers, and you can use those. It's not a complete exhaustive set, but there's a half a dozen that people, I think, use by standard. Now, the only comment on the approach you developed is that it does require analytic source functions, correct? Because you have to take derivatives.
Yes.
So if you have a tabular equation of state, for example, or tabular cooling function, then how do you handle that? Can you handle it, or?
I think you can. So the way I implemented this in my code is right. So you have to have the tabular function has to be accurate enough so you can do the derivatives, and then you can handle everything. You can do the integration. You can do you can incorporate the information numerically. So you can come up with the.
So you need a function that has derivatives tabulated.
Yes. Or you can calculate it on the
fly.
With some spline
So for example,
interpolation or some interpolation scheme then in the tabulated data.
Right, you have to handle the numerics. For example, when I do the cooling with the with the methods, I have to use the tabular functions from Nordita to retain something. And so I use that stiff scheme to incorporate the cooling function, but it's all done, the derivatives and everything is done numerically. It's not very expensive compared to the higher units.
Okay, I think we should wrap up here and hope that the barbecue.
Yeah, so maybe I should keep you updated. So the rain is actually not too bad, maybe just gone now. So the students are already cooking, there's some food. And in case it rain again, then we will just move indoor into the auditorium building. There is a conference inside. So yeah, so we will still have a barbecue.
Okay, thank you everyone.